The other option we have with trig integrals is we can turn things into polynomials by using t results, and then use our techniques for integrating polynomials. Might be partial fraction, might be whatever. So remember, t equals tan x on 2. What happens to our derivative? Well, we know that sine x, I'll substitute in for sine x, 2t on 1 plus t squared. Cos x, I'll substitute in 1 minus t squared on 1 plus t squared. Usually these are integrals that involve sine and cos, but I suppose you could use tan as well if you wanted to. But really, substituting a t result in for tan, all you're really doing is using a double angle result, if you think about it. So, t dx would become a half sec squared x on 2. Sec squared is 1 plus tan squared. And so that becomes 1 plus t squared. So we end up with dx equals 2 to t on 1 plus t squared. Now, the reason I've boxed those two, we don't go through that derivation each time, because after a while we'll just remember, okay, if I'm using the substitute, it's like another t result, if you like. If t equals tan x on 2, then dx is 2 to t on 1 plus t squared. Okay. So something like this, dx on 7 plus 6 cos x. This is where it becomes useful, because I've got cos x in the denominator, but there is no way I can create the derivative there. I mean, how do I all of a sudden make a sine x? I could make a sine squared, because I could change the 1 on top to sine squared plus cos squared, but that's not really going to help me. So we'll use our t results. So t is tan x on 2. That means dx is 2 to t on 1 plus t squared. Substituting in. And of course, the nice thing about using it for sine and cos is the denominators turn out to be the same. So whilst we've got fraction on fraction, we can easily tidy that up by multiplying everything by 1 plus t squared. And I end up with 2 to t on 13 plus t squared. That is a standard integral. It is, of course, inverse tan. A squared, in this case, a is the square root of 13. So I'll have 2 times, in this case, we do have 1 on a out the front. So 2 on root 13, inverse tan, t on root 13. The big mistake, I guess, is to stop there. But remember, the original question involved x. So now we substitute back in for t, and we get this rather interesting expression of 2 on root 13, the inverse tan of tan x on 2 root 13. No, you can't cancel the inverse tan with the tan because of the over root 13. So it's not going to just cancel. So we leave it like that. What a lovely little expression. Now, you don't have to be limited to cos x and so on. If you use the substitution t equals tan x instead of tan x on 2, so maybe the angle was cos 2x, and so you want to use t equals tan x rather than tan x on 2. It is going to change our derivative. Let's have a look at what happens here. The t dx will be sec squared, which is 1 plus tan squared, which is 1 plus t squared. And so dx is dt on 1 plus t squared. Basically, whatever happens is, if it's x on a, and there's the generalized differentiation of that, we will end up with dx is a dt on 1 plus t squared. So that's why when our standard one is tan x on 2, so a is 2, so we used 2 dt on 1 plus t squared. But if you wanted to use it for, say, tan x, x on 1, that would be 1 dt on 1 plus t squared. And so on and so on. As I say, most of the times it will just be x on 2, but that's not stopping you using it for other situations if you want to. See, look, A matches A. Okay, so we'll just add a couple more questions there for our trig.